Good day class. We will understand three-phase power with this week's series of video lectures. In this lecture, we will learn how to analyze a three-phase circuit. We will first define the power in a balanced three-phase system, then derive the load transformation from delta to Y, and finally, we will define the steps for a per-phase analysis. The single-phase complex power equation is given as S is equal to VI conjugate. For three-phase power, we can say that the complex power is a summation of the individual single-phase complex powers. Thus, this can be written as S three-phase is equal to VAN IA conjugate plus VBN IB conjugate plus VCN IC conjugate. When the system is balanced, we can write this as follows, which gives us 3 times VAN into IAA conjugate. Thus, we can say that the three-phase complex power for a balanced three-phase system is 3 times the single phase complex power. We can further expand this into real and reactive power. Here, the three-phase real power is 3 VAN IN cos theta, while the reactive power is 3 VAN IN sin theta. Let us now look at the delta and Y connected three-phase loads. For the delta connected load, we can write that the apparent power is equal to 3 times VAB into IAB. For the same load, the line voltage is the same as the phase voltage, while the line current is √3 times the phase current. Substituting this, we get the three-phase apparent power is √3 times V line into I line. Similarly, for the Y connected load, we can write that the apparent power is equal to 3 times VAB into IB. For a Y connected load, the line current is the same as the phase current, while the line voltage is the √3 times the phase voltage. Substituting this, we get the three-phase apparent power here also as √3 times VL into IL. Here VL and IL are the V line and the I line. Thus, we can see that irrespective of the type of the load, we have the same three-phase power formula for both Y and delta connected loads. Next, we will see how we can convert a delta connected load to its corresponding Y counterpart and vice versa. The idea here is that if I want to find an equivalent Y connected load for the given delta connected load, the line current and the line voltages of the load will not change. Let us analyze the two connections separately and then combine the equations. We know that for a delta connected load, the phase current is the line current divided by √3, while the phase voltage and the line voltage are equal. We can find out the complex impedance Z delta as VAB divided by IAB, or by substituting the values from the above, we can get Z delta is equal to VAB divided by IA divided by √3. This gives us VA divided by IA as Z delta by √3 as equation 1. Now, for a Y connected load, the phase voltage is the line voltage divided by √3, while the phase current and the line current are equal. We can find out the complex impedance ZY here as the VA phase voltage divided by IA phase current. Substituting the corresponding line values, we get Z delta is equal to VAB divided by √3 divided by IA. Thus, we can write here that VAB divided by IA ratio is ZY into √3. Equating these two equations, we get Z delta by √3 is equal to √3 times ZY, or Z delta is equal to 3 times ZY. Thus, if we have a Z delta connected load, we can find the equivalent Y by dividing it by 3. Now, if we have a balanced three-phase circuit, we can say that the neutral current IN is IA plus IB plus IC, which is equal to 0. Thus, we can represent the three-phase circuit as just one phase here, and we can draw it as below. We can solve this single-phase circuit as per normal single-phase analysis to find out the different voltage and current parameters. Just to make it more clear, let us go through the steps for per unit analysis. First, make sure that the three-phase system is balanced. That is, the three-phase sources need to have the same magnitude with 120-degree phase difference. And also, the three-phase impedances must be of the same value, both phase and magnitude. Next, convert all delta connected sources and loads to their corresponding Y connected sources and loads. This reduces the three-phase circuit to a single-phase circuit. We can apply the same concept used in single phase to solve for this three-phase circuit now. In this lecture, we understood how to derive the three-phase power for a balanced system, understood the delta Y transformation, and laid out the steps for per phase analysis. We can also list out the formulas we encountered for the delta and y connections as follows. Here, PS denotes the per phase value and line denotes the line values. Thank you.